The Royal Aircraft Establishment is the main Ministry of Defence centre for aerospace research and development in the United Kingdom. With the headquarters and main establishment at Farnborough, there is a large outstation on 2 sites near Bedford and 3 ranges: Aberporth on the west coast of Wales, West Frew in southern Scotland, and Larkhill on Salisbury Plain. RAE's responsibilities cover most military aircraft and weapons systems, both offensive and defensive, including air defence, long-range strike, medium-range ground attack, and close support. All aspects of helicopter technology are covered for operations on land and over the sea, as well as surface-to-air, air-to-air, and air-to-surface weapons. In addition, the establishment provides support for civil aircraft projects, including long-term studies on structural fatigue, and a continuing program of work on advanced landing systems, particularly for operations in reduced visibility. RAE also has some responsibility for the UK involvement in space, working with the European Space Agency on multinational projects and with the Science Research Council on scientific satellites. Facilities exist for receiving data from and transmitting commands to satellites in orbit, and for the manipulation of the data received to reveal information on the resources and features of the Earth.
Now I would like you to use the cursor control to outline the area that you would like to look at. Okay, here's your piece of the history.
Can we separate the land from the water?
Okay, you can now slice band 7, pick out the water, down by the coast.
Yes, that's the water coming in from the North Sea.
With the exceptions of engines and radar, the Royal Aircraft Establishment has responsibilities for R&D in all areas of aerospace activity. Aerodynamic research is a major activity at RAE, and the establishment rightly enjoys a worldwide reputation for its advanced work in this field. Its range of wind tunnels is unequalled in Europe and covers the complete range from low subsonic up to very high supersonic airspeeds.
Let's wait a little bit. Okay, it all looks steady. Okay, Bob, can we go to 0 degrees instance, please?
Okay.
Let's take a data point of that. I'm going to have a look at the output.
With the advent of multinational collaborative projects, RAE engineers and tunnel staff frequently work in close collaboration with similar engineers and technicians from other European countries.
Minusbereich für Einigung.
Minis, na. 100 Millivolt haben wir. Wenn wir ein bisschen knapp in der Zeit werden, fangen wir mal in Watt.
I think we need another point in here. What do you think?
The most recently developed facility is the 5-meter tunnel. This large pressurized wind tunnel has been designed to improve the accuracy and reliability of tests on the aerodynamic behavior of future aircraft in the low speed range, mainly during takeoff and landing. To combine low speed landing and takeoff with high speed in flight, designers have had to develop complex high lift devices such as slats and slotted flaps to achieve the required performance. For tests on future combat aircraft, the tunnel uses 1/3 scale models. Increasing the pressure inside the tunnel to 3 atmospheres persuades the air the model is full size. The data obtained then properly reflect full-scale values. To prove the tunnel, close comparisons have been made between tests on a model of an A300B and the behavior of the real aircraft in flight. Aerodynamic research is not just mathematics and tunnels. There are areas of research which have to be explored in as near the operational manner as possible. In some particularly dangerous flight regimes, quite large-scale models are used in studies of dynamic behavior at extreme attitudes, beyond the stall and in the spin. Data are obtained by means of telemetry from onboard sensors and from kinetheodolites. This specially instrumented NAT aircraft is gathering information on low-level turbulence as it relates to terrain. A mathematical model of atmosphere near the ground can then be constructed, the long-term objective being a smoother ride at low level. Paradoxically, the previous generation of aircraft is often the most convenient way of developing any future generation of flight systems. This Hunter, for example, has two completely separate and quite different control systems. First, there is the original and traditional direct manipulation of the aircraft's control surfaces by the pilot. But in the other seat, between the pilot and the control surface, there is a computer system known as active control or fly-by-wire, because the optimum control movements for any situation or maneuver can then be generated. Alternatively, a third very small side stick works by signaling forces instead of movements to the computer. By means of sensors in every part of the aircraft and a multiplex system of cross-correlation of signals, the computer continuously monitors and controls every aspect of the aircraft's response much faster and more comprehensively than any human brain. The key to the technique is in the control laws written into the computer software which governs the system. The main thrust of development is in devising and testing these laws for all conditions of flight. As in many other programs of research, work on active control follows the classic RAE pattern of taking mathematical simulation one stage further into flight simulation, this time with a pilot in the loop to provide informed feedback before trials in the air.
Oh, another spike.
I'm going to climb up a bit, and I thought in that sort of task where I require flowing sort of flying, that it was about to show up as a twitch in it. Well, the tracking task, I thought it was a lot better. Nicer control system altogether. I'm finding I've got a smoother control of the aeroplane.
Further developments in ACT are being made in the collaborative demonstration program between RAE and British industry on an active control Jaguar aircraft. This Jaguar test rig is being used to investigate and prove the electronic and mechanical systems involved.
It's alright, I'm away. Except that I've got negative height on.
Are you pressing the
Especially the wrong button, that's
freeze?
better, yeah.
Freeze instead of reset.
Major advances have been made in the development of small but powerful actuators to operate the tailoron control surfaces with the very high rates of response required for active control. The benefits of active control are improved handling characteristics in every area of the flight envelope and should dramatically ease the pilot's task in all operational flight regimes. Reducing workload and ensuring an acceptable working environment for aircrew is an essential part of RAE's work. In military flying, the overall effectiveness of the system is highly dependent on the human operator. Special work-study techniques have been developed at RAE to analyze and describe the ergonomics of operational flying. Fundamental studies are carried out on cockpit heating, protective clothing, oxygen supplies. In fact, all aspects of the physical environment and their effect on performance.
Yeah, okay, you feeling alright, Dave?
Yes, no, it's fine.
Okay, bringing you up now.
Vibration research, for example. How well can a pilot perform even simple tasks when his eyes, hands and internal organs are subjected to this, as they would be under certain flying conditions?
Here we go then.
Right, 10 degrees of climb.
The results of these and other research programs are embodied in a functioning mock-up of an advanced future cockpit design. ergonomic considerations have led to new proposals for the layout of the many controls required. Radical developments in cockpit displays are aimed at ensuring that the right information can be shown exactly when the pilot needs it and in a form he can easily assimilate.
But it's quite easy to hold it.
The overall objective is greater integration and automation of the crew interface with the total avionics package.
Yes, it's still tracking across, and it's also writing cursively at the moment.
Mike Papa Delta X-Ray Foxtrot, this is Cove Radio, roger, go ahead.
About 7 miles from Farnborough is the Cobbett Hill radio station. Its extensive aerial systems feed into advanced communications equipment, the trial's engineering link, and a measurement system which records and analyzes data from the trial itself. In the air, a flying laboratory has a variety of prototype radio communications devices and trials equipment. The trend is firmly towards digital data transmission, which has a built-in resistance to enemy jamming. Future in-service systems will of course be much smaller, but the principles of passivity, speed, and automatic channel and frequency tuning are being proved here. A flying laboratory is also used for navigation work. The trend here is towards integration of a variety of navigation systems in order to provide higher reliability and greater resistance to interference. Radio aids, inertial platforms and satellite systems all have a part to play. Navigation trials often include the use of the high-precision tracking radars at Aberporth to measure the effectiveness of the on-board systems during trials. After the trial, data from the aircraft and from the radars and other sources is correlated for more detailed analysis. Closely allied to both radio and navigation work has been the development of sonar techniques for submarine detection. Nimrod Mark II incorporates a new sonic system developed jointly by Britain and Australia.
Navigator, acoustics 2. Clear. Weak contact in on Beaufort 26.
Complex processing, making use of massive computing power and novel displays, can handle simultaneously signals from a wide range of sonar buoys in the water. One of the more unusual facilities developed by RAE is the research vessel Colonel Templar. A converted stern trawler, the ship has been extensively re-equipped to meet the requirements of the experimental development and testing of specialized sonics devices. Hydrophone signals, transmitted from buoys in the water, are recorded and analyzed in the main laboratory area on board. The problem of sensing and presentation of data is a dominant theme at RAE. The big growth area is electro-optics. This hunter has been fitted with a sensor in the nose of the aircraft, and in the cockpit a head-down screen which can also be projected into a head-up display. During flight trials, the test pilot's exterior view is blanked out by means of filters, the objective being to prove the feasibility of high-speed, low-level night flying using this kind of visual information. In this particular instance, the information is provided by means of low-light television. However, the sensor with the most potential is thought to be infrared. With modern infrared imaging systems, the very high picture quality derived from the IR scanner's sophisticated optics is comparable with that of visible light, even in the dark. FLIR, which is forward-looking infrared, is a major area of research. This Sea King is another flying laboratory, designed to prove the system in the air and to solve human factors and systems engineering problems for the design of the in-service hardware. The main benefit of FLIR is its ability to see in the dark. With a FLIR display, the pilot can fly almost as easily by night as he can by day.
normally you've gone through the...
For all of these systems, RAE has responsibility for many aspects of research and development, working in close conjunction with industry and other defence establishments.
The latter test, this is an ADMC, and to maintain the ADMCs further, more sophisticated laboratory test equipment has been defined and will be required before...
In fulfilling this role, RAE project teams advise the armed services and the Ministry of Defence headquarters from the earliest conception to the final acceptance and in-service use.
An agreed schedule of acceptance tests, engineering tests on the equipment before you start any development work.
The weapons RAE deals with include surface to air from both land and sea, air to air, both attack and defence, and air-to-surface attack weapons for targets on land or sea, and including bombs as well as guided weapons. Much of the intramural research on weapons is concerned with missile homing heads and guidance systems. The establishment is deeply involved with industry in this work. Particular attention has been paid to further development of the cluster concept. Both the type of sub-munitions carried and methods of deployment have required very careful consideration to meet new operational requirements. The problems of air-to-air combat are complex. Advanced systems are required to aid the pilot in target acquisition and to successfully achieve a kill.
The first target should be appearing very soon. There is a delay between when I press the button up here to when you see the response in the dome, and it will be projected for 10 seconds. That's correct call.
A piloted combat simulation is used in which an image of an enemy aircraft is generated and maneuvered to represent a realistic engagement. For the design of the guided weapons themselves, as in other areas of research, mathematical modelling plays an important part.
A missile which is being rolled with a zero.
Literally thousands of weapons firings can be simulated in a short space of time. As well as helping to decide the best operational use of the weapon, simulations have a direct bearing on the planning of expensive but very necessary test firings.
Does the storage display scope give you a better view?
I think it would. In fact, we can look at the trace and work out the variation in velocity of the missile.
To carry out weapons trials safely and effectively, RAE has developed several ranges, the largest of which is Aberporth. The range encompasses some 1,600 square miles of sea area and caters mainly for missile firings from ships at sea, shore-based launchers and from aircraft. Aerial targets are deployed from Llanberra, 50 miles to the north, and include the recoverable subsonic Jindavik and the expendable Stiletto supersonic target air-launched from a Canberra. Although development work is the primary purpose, acceptance trials, service practice firings and other air systems trials flying are also important. Aberporth also provides a centralised information processing and data reduction service to the main establishment and the other ranges. West Frew is based on a fully operational airfield and includes a small land target area on the coast of Luce Bay, as well as about 150 square miles of the sea area of the bay itself. The range is particularly suitable for high-speed, low-altitude aircraft sorties, which require full instrumentation cover of either air-to-ground or air-to-sea attack weapons and their associated aiming systems. RAE Larkhill is a fully instrumented land range and is used for trials requiring fixed or moving surface targets such as tanks.
Range square feet 1011 millibars.
It is particularly suitable for exercises where terrestrial features can make aiming difficult.
7, 6, 5, 4, 3, 2, 1, 0.
Hitting the right target with the right weapon system is what it's all about, of course. But what should the right system be in, say, 5, 10, or even 20 years' time? The answer is not easy. Technology develops, threats change, priorities alter. But the future of air systems is RAE's business, and the essence of its collective function is to ensure that the right choices and decisions are made. To exemplify the establishment's role, consider the problems and the technical options involved in just one area of operations. For the foreseeable future, there will continue to be a requirement for ground attack behind the enemy's front line of battle. Jaguar and Tornado handle it now, but what comes next? To find the right answers means asking the right questions. A few, multi-role, large and complex? Or many more, specialized, smaller, simpler? Sophisticated missiles? Or less expensive, but perhaps less effective area weapons? Can one man cope with the demands of modern war? Or must we have two to retain some flexibility in the face of the unknown? Before the design process can start, there are many such issues which have a direct bearing on the most basic considerations of all up size and weight in relation to performance, range and weapons carried. Crucial factors are power-to-weight ratio and aerodynamics. Hanging several tons of bombs or missiles under an aircraft can dramatically alter its performance and flight characteristics. The effect is being very carefully considered in wind tunnel studies and in full-scale flight research. When the results of tests like these are combined with fully developed active control, then not only might aircraft handle more easily and have a better performance, they could look very different as well. To avoid detection, operational flying is very low and very fast. Just piloting the aircraft is a highly specialized technique. Major factors in the design of such aircraft are controllability and strength. Many years of research into materials and structures has built our awareness of what can be reached in the future. On structures made from carbon fiber composites, for example, methods of design and fabrication are being studied to yield the maximum benefits with minimum weight and reduced costs. Defects in these materials differ significantly from those found in metals. New methods of ultrasonic inspection have been devised to ensure that high standards of quality are maintained. Careful analysis of composite structures is required to ensure design strength is achieved, and microscopic analysis of failures is essential to the development of new materials and structures. One of the keys to effective ground attack is perfect navigation. While in-service hardware is very good, tactical low-level flying gives a very hard ride to sensitive nav attack systems. One line of development has been based on the design of more robust systems. The ring laser gyro has the potential to withstand the physical shocks involved, and development is now moving towards a fully engineered in-service system. Into the war zone, over the battle area, where there are bridges or concentrations of supplies or reserves, there will certainly be similar concentrations of enemy radars, guns, and surface-to-air missiles. This is where the dark arts of electronic warfare hold sway. To the aircrew, this is what a hostile radar environment sounds like. A passive warning system indicates they're being illuminated. If it stays on too long, there may be problems. Electronic countermeasures effectively jam enemy radars and confer great tactical flexibility on the attacker. To evaluate future systems, RAE have developed a radar simulation facility which duplicates precisely a wide range of likely defensive radars in order to measure the effectiveness of our own countermeasures.
Well, we're still tracking. No, we've lost lock. Off lock. Back to search. Sorry, back to search.
The great benefits of very low and fast flying are avoiding detection and the element of surprise in attack. The great problem is that just as they can't see you, you can't see them until it's almost too late. At a closing speed of nearly 300 meters per second, target acquisition is extremely difficult. In practice, the pilot has less than 10 seconds to complete all phases of the attack sequence.
100 feet, 450 knots.
How did you find that one?
The flying is the difficult bit.
Yes.
The fact that this simulator's got little or no feel.
To improve effectiveness and to enhance survivability of the aircraft, an ideal solution could be the so-called fire and forget missile, where the pilot would simply indicate the target and commit the weapon. The system then takes over, automatically capturing the target, initiating release, and homing in for a precise hit. An added complication is the question of night attack. Darkness is the traditional cover for movements, regrouping, and resupply. This is why forward-looking infrared is thought to be essential for the systems of the future. Ground attack is only one mission. There are many more. Each demands just as detailed consideration by experts in order to balance the operational advantages of the various new technologies against the overall cost effectiveness. Only by maintaining expertise over its entire range of responsibility for future air systems can RAE make sure the right technical advice is available whenever it is required. Through its developing relationship with the armed services and with industry, and using its range of facilities and experience, RAE continues to make a unique contribution to the development of airborne systems for national defence, and helps to sustain the UK capability for advanced aerospace technology, which is so vital for the future.